So, in terms of the calendar, today we cover something called the second fundamental theorem of calculus, or part 2 of the fundamental theorem of calculus. Project number 2 is currently outstanding. Does everybody have a copy of that project? All right, so that project will take some time, so make sure you give it some time. I think it's a really good project, but make sure you have time to do it. At the moment, it is due on February the 11th, which is Monday. I don't know if we're going to have school on Friday. I think there's a lot unknown about the weather coming up, but if we don't have school Friday, then everything here will get pushed down a day. I will reprint this calendar and give it to you when next we meet. So the project would be due a day later. But anyway, this is the current schedule, and we have a quiz coming up tentatively a week from today, but it might get pushed back as well. Any questions on the calendar? Ofer. There's room at the end of the semester. There we got two to be announced days, so we can handle a snow day or two. Okay, so that is that. Next thing I wanted to talk about, can you open to page 24? That's where we start today. But I do want to talk just very briefly about the quiz. So here's what I want to say about the quiz. The very first question on the quiz talked about finding the derivative of cotangent. Now I think that some people thought it was mean for me to put cotangent on the quiz, given that cotangent is not on the reference sheet. So let me say that well, I probably am mean independent of this cotangent question, but when I wrote this quiz, I wasn't thinking about what was or was not on the reference sheet. I was making some assumptions, and it's my fault for not making these assumptions clear to you. The assumptions that I'm making for students that are here, gotten through Calc 1 and are now in Calc 2, is that you have a handful of derivative rules just memorized, just ready to go, independent of a reference sheet. So for example, the derivative of any polynomial, I expect you to be able to do. The derivative of all 6 of the trig functions, including cotangent, I expect you to know. The derivatives of e to the x, a to the x, ln of x, I want you to know those. There are a couple of inverse trig functions whose derivatives I'd like you to know. Inverse sine and inverse tangent, that's probably enough. And then product rule and quotient rule, and most importantly, which rule that allows you to take all the basic derivative rules and apply them to complicated functions, is the chain rule. So I have all of these things that I'm assuming that I wrote the quiz assuming that we had all of these things just ready to go. So I wasn't thinking about what was or was not on that reference sheet. And again, I should have been clear about this assumption. So what I think we're going to do in the next week and a half or so is take a quiz where I will, between now and then, I will give you a reference sheet that has a list of exactly the derivative rules I expect you to know. And then I will give you the quiz later on with the same reference sheet, or the same sheet, but with the answers blanked out, okay? So again, I will be very clear. It's not going to be a pop quiz, but I will be very clear exactly what I'm hoping that you have available to you. Vince? The derivative of cotangent is negative cosecant squared. Whole question. I have negative cosecant squared of 3x to the negative 8 times 24x to the negative 9. Answer key is here. You can pass that around if you're interested. Okay, so that is that. Right, yeah, I think that's good. Okay, any questions on what's coming? It's not well formed yet in my mind. I've only just begun to think about these assumptions and what I really want to make sure that you know. In general, I'm not a fan of just let's memorize everything under the sun. But this semester, quite a bit of it anyway, is focused on antiderivatives. And I'll say that, see if I can write 3 things up here. The integral of secant squared dx compared to the integral of sine squared x dx compared to the integral sine squared x cosine x dx. And then 2 more for good measure. You don't need to write these down, but we will see all of these integrals this semester. And I will say that if you have memorized this list of derivatives that I want you to have memorized, then 2 of these are easy. They're just immediate because they're on the list. What's the, whose derivative is secant squared? It's tangent of x. So that one is really easy and it's just done. To integrate sine squared of x, well, it's not on our list. We need a technique, and we'll have that technique in a few weeks. To integrate sine squared x cosine of x, that one looks harder than sine squared. It's actually easier than sine squared, but again, it requires a technique. But if you don't have, like we're going to learn all these techniques this semester, right? But if you don't know that secant squared is an easy one, you're going to maybe try to apply some of these techniques that we'll have to something that's easy. But you're only going to know it's easy if you just have readily available this standard list of derivative rules, okay? Same kind of thing over here. One of these guys is easy. Anybody recognize one of them is the derivative of a function that we know? It's the one on the top. That is right there, the derivative of arctan. It's easy if you have that readily available. The one on the bottom looks almost the same. It requires a whole new technique, has nothing to do with arctan. And again, like if you don't have those derivatives readily available, there's no way for you to parse out what are the easy ones and then what are the ones that are going to require these techniques that we'll develop in the coming weeks, right? Okay, so let's go back to the previous page here. So 24, and we'll go over there and start with Joey at the very bottom. Okay, thank you. So let's move on to the next page. So in this morning's class, spent probably a good 50 minutes working through this activity. And the beginning parts were okay, but then things got a little bit hairy for most of the groups, and I wasn't thrilled with the way the class ran. So we're going to try to do this a little bit more together. Some of you guys in your groups, but a little bit more together to make sure everybody's on the same page and getting the ideas that are important. So let's start with number 1. Josh. Okay, so let's see if we can do this together. This is quite similar to one of the questions on the quiz. So again, this function right here is little f, and we're trying to graph capital F. And there are some things that we discovered before. From here to here, and from here to here, that function has a certain property. What property is true in both blues? It's positive. And if the derivative, that's this guy right here, I'll write the word derivative. I don't want to call it f prime because that's not the notation in the problem. But this is, we're thinking of it as a derivative of something because it's convenient for us to do that. If the derivative is positive, then what is the antiderivative doing? It is increasing. I meant to write derivative greater than 0 there for positive. And the same kind of thing, I want to say conversely, but that's actually not the right word. It's inversely. If the derivative is negative, then the original function is decreasing. But then there was some other stuff that we could say. So I'll draw down here in the red the negative part. But then we've got different property. What is true about this function from here to there? What's true about the entire purple part? About the original that we're looking at here? It is decreasing. And if the derivative is decreasing, then the original function is concave up, right? Sorry, concave down. Yeah. So if this guy is decreasing, if the derivative is decreasing, then the antiderivative is concave down. Right, we discovered this a couple of classes ago. So we're going to ask you to draw our antiderivative in that blank graph. There's one point that tells you where to start, because otherwise you could start anywhere. So we're going to start at -4, 0, so just put a dot there. And then take about 30 seconds to see if you can sketch our antiderivative. It's got to be increasing in the right spots, decreasing in the right spots with the right concavity, and then check with your neighbors. So hopefully we came up, I saw lots of graphs that looked quite similar to each other. It's something which is increasing until about -2 point something, and then decreasing, and then the concavity changes I don't know exactly where it goes. It might hit above, it might hit below. I'm not saying it hits the origin or that it hits where I've drawn it. But then the concavity changes and it decreases until we get to like 2.2 and then going back up, right? So very rough. Don't really have a sense of how high the high is or how low the low is. But we do have a way to actually figure out how high the high is and how low the low is. And several people naturally jump to that way. What can we look for on this original graph to tell us how much we gain, say, from going from -4 to -3? We're looking for the area, right? The area. That's how much we have gained. So we're gonna do something that we've done before. That is just calculate area, but we're gonna write it in a slightly different way. So here's how we're gonna write it. Number 2, we are over to Tony.
Area function C of x. This function is defined the following way. C of -3 is the area between the above left curve and the x-axis from x equals -4 to x. C of -2 is the area between the above left curve and the axis from x. Areas below the x-axis are negative.
Okay, so really I shouldn't have been saying area, I should have been saying signed area. And the way that we write that symbolically, so this is just what Tony was saying before, but in symbols, this function right here, this new function, the cumulative area function, for C of -3, we go from -4 to -3, and we just find the area. For C of -2, we go -4 to -2 and find the area. Always starting at what number? -4. That's just our starting point, and it's kind of arbitrary, but we're just saying let's start at -4. Okay, and so then we've got this brand new function right here, which says if you want to find C at a particular number, you just look for the area from -4 up until wherever you want to stop, whatever number you're looking at. So let's do a couple of these together, and then we'll divvy up the work. So first one I want to find is actually C of -4 to fill in this table right here. So C of -4, according to my yellow highlighted thing, is the integral from -4 to -4. How much area do you get when you don't sweep at all? You get 0. So in some sense, that guy right there is our starting point, -4, 0. Okay, and I just picked -4. So that's part of the givens of this problem. Okay, so now we're going to look for -3. We're going from -4 to -3, which is this part in here that I've highlighted in red. And all I'm interested in is estimating the area inside of that space. So let's estimate that area together. So the area here. So we can cut it into a triangle and a rectangle. Is that fair?
Yeah.
Nobody seems to like the trapezoids, but we'll cut into the rectangle and triangle. Okay, so the area of this rectangle, careful of the scale over here if you're just counting boxes. What's the area? It's 4, right? Every box is actually worth 2. And then for the triangle, we're doing half base times height. Yeah, maybe around 3. Depends on how high we say this thing goes. So if we call it 10-ish. Everybody all right with that? Something around 3. Okay, so then the total area there is 7. And is that positive or negative? That's positive. So the very first number we're putting here, which is the area from -4 to -3, is 7. And let's do one more together, and then we'll split up the rest of the work. Let's go ahead and do the next part, which is from technically from -4 to -2. But I don't want to recalculate that 7 every time I see it. So I'm just going to go from -3 to -2, which means I got that little part there, and then this part up here. Now there is some cancellation happening here, but that triangle that's down below is pretty small. I'm happy to ignore it. You guys okay ignoring it? just to make this quicker. Again, it's all approximations anyway. So what if we just pretend that we've got an entire triangle like that? I know that I'm going to be overestimating, but let's just make it easy. So half the base times the height, what's the area of that thing? Looks like it's about 2 for that triangle. If you feel badly because we overestimated, then call it 1.5. Again, it's just rough. So let's call it 1.5. Is that all right? So the area here, after we took off a little bit because we overestimated, it's about 1.5. So how much is the total area then, red and purple? 8.5, and that's fine, and that's going to be the answer. But how about we maybe don't go all the way back to the beginning again? Are you guys willing to say that we had 7 already, and now we're just gaining 1.5 more? Like, I like to think of it as just adding on to stuff that we've already got. So I think this one down here will become 8.5. Okay, and now just to save a little bit of time, we're going to ask people to calculate different areas. So split up the work in your table. You don't need to worry about filling in the numbers first, just the areas, just calculating areas. So there are 6 of them left. Maybe everybody at a table can do 2 areas. Just split up the work, and then we'll get some numbers, and then we'll fill in the table. So again, it doesn't have to be exactly those numbers, but should be something close to those numbers. And then once we have the numbers, well, I guess actually I can write in the rest of these. I do have a symmetry thing happening here. So now I've got all of my gains and losses with my areas. But now we should be able to fill in the rest of the table. So for example, if we're currently at 8.5, and then we lose 2.5 because we were below the x-axis, then we land on 6. So go ahead and fill in the rest of that table now that you've got the area. So stop calculating area if you're still doing that, and just fill in the rest of the table. Did I do that right? Does not look like I did that right. Any questions on filling in the table? Okay, so now that we've got the table filled in, you have about 9 points that you can plot. So go ahead and plot these points on that grid to the right, and then connect the dots. So we plot our 9 points, we connect the dots. What do we notice about this graph? It does look like a cubic. What else do we notice? Yeah, doesn't that look like the first one that we did? The graph that we made up above, this was a very rough sketch. All that we looked at here was increasing, decreasing, concave up, concave down. But we know that we can be more precise than that by thinking about this area idea. And really the only new thing here is that we can think of this area accumulation as a function, a perfectly legitimate function on its own right. Okay, any questions on that? Are we surprised that it doesn't have the, like, isn't it kind of strange that it starts here at -4, 0, but it doesn't end at 4, 0? I mean, the graph up there is symmetric, no? Why does it end higher? Good. Yeah, it's symmetric over the y, but not over the x. If it were going to end at the same exact spot that it started, what we'd be saying is that this negative area perfectly cancels with this positive area, and just look at it, doesn't look like it. Looks like there's a little bit more negative than, sorry, a little more positive than negative. So the symmetry can be a little bit deceiving. Okay. If we did, if we made sure it went through 0, if we made sure it went through the origin, then it would be symmetric. Oh, that's a good thought. Is that right? Yeah, I still think, what am I saying?
Not the original function.
Yeah. Hmm. So the last thing in this activity here is actually me giving away the game and telling you what the rule is for this guy. It looks like a parabola, and it is. So we can actually figure out exactly what it should be over there. But for right now, we're happy enough with approximations, and we'll go on to number 4. Number 4 says we're going to define that c of x, the cumulative area function, a little bit differently. We're going to have the integral going from 1 to x. What did the integral go from before? Went from 4 to x. Sorry, negative 4 to x. Right. So this starts a little bit differently. Let's go ahead and see if we can fill in the one easy number in this table. There's one number that we don't have to do any work for. What value of x is an easy one to calculate? Is 1. Because if you're finding c of 1, you're finding the integral from 1 to 1 of the function. And how much area do you get? If you don't sweep it all, you get 0. So that's an easy one. Now let's go ahead and move to the right. Let's finish the rest of this table going to the right. So the numbers that we had from before, these areas are still the same, right? It's the same picture that we're starting with. It's still this parabola looking thing. So all of these blue areas are the same. So what effect does that have? Well, let's just jump to the right. Going from 1 to 2, how much area did we gain or lose? We lost 2.5, and then we gained 1.5, and then we gained 7. It's still true, lost 2.5. So this, I'll put them down here in blue again. So we lost 2.5, gained 1, and then gained 7. So where do we go in this next box right here? After 1, 0, we have 2, negative 2.5, right? We just lose 2.5 from 0. And now we're going to gain 1, so we land on negative 1.5. And now we're going to gain 7, 5.5. So far, so good? What's that? Did I make a mistake there? Was it a 1.5? Thank you. Okay, so let's fix that. Okay, so then where do we land if we are at negative 2.5 and we gain 1.5, and negative 1, and then we gain 7, 6. So far, so good. Now let's go the other way. So let's do one of these in slow motion. C of 0, according to this function, is the integral from where to where? Yeah, this one always starts at 1 and it goes to whatever x is, which in this case is 0. And why is that integral a little bit disconcerting? It's backwards. So how do we switch it to make it the right order so that area means what we expect? You make it negative. So we're doing that just because our ideas about the integral representing area are only valid if the numbers are in the right order, small on the bottom, big on the top. So the integral from 0 to 1, ignore the negative sign, but that integral from 0 to 1 represents an area, a signed area. So let's look between 0 and 1 on our original table here. Between 0 and 1, what was the area? It was negative 4.5, yes? So when we come over here, we get negative 4.5. Right? So how much is that? Positive 4.5. Okay, so what number do we have on this other side? It's 4.5. Okay, now the next one is going to be a little bit trickier. We're going to start it the same way. Let's try the next one. So the next one for me is C of negative 2. Maybe it won't be trickier. C of negative 2. According to our definition, that's the integral from 1 to -2. How did we go wrong here? Did I do something wrong? 1 to 0. Did we skip something? Skip -1. Let's do -1. And I don't like that because the numbers are in the wrong order. So again, we'll put them in the right order, small on the bottom, big on the top. And how do we pay for that? There's a negative sign. Now let's take a look at that integral because we have that information on the previous page. That integral represents the area from -1 to 1. So let's look at the area from -1 to 1. So from -1 to 1, first we lost -4.5, and we lost another -4.5, right? This is the first time that we're stacking them because now we have an interval that's more than just 1 unit long. So how much is the value of that integral? Is -9. Okay. The integral from -1 to 1 is just that total area, -9. So we come back here, and we say this integral is -9, which is 9. So that guy up there is +9. Okay, now I'm kind of tired of playing this game. So let's see if we can get to the answer a little bit quicker than repeating this over and over again. Let's go ahead and take a look at the actual changes. I've written a few of them. See, like those are the easy ones because they were all bigger than 1, so we didn't have to do this funny change the order on the integral sign. But what was the actual change going from 4.5 to 0? It was -4.5, yes? Lost 4.5. What was the change going from 9 to 4.5? It was also a -4.5. So this is like an after the fact. Let's see what the changes were. And can we look at that and compare those numbers to the ones on the previous table? How do these numbers compare to the ones that we had written there before? They're the same. These numbers are exactly the same. In some sense, it doesn't matter that the limits are maybe in the wrong order. And this is kind of a surprise, is that the numbers are exactly the same. That's right. All we're doing is changing a starting point, like a reference point. So if we believe that this pattern will continue, then let's just go ahead and fill in the same numbers from before. So what was next after -4.5? Positive or negative? -2.5, and then 1.5, 7. And now we can fill in, I think, rather quickly the rest of this table. But we got to be careful. We landed on 9 after losing 2.5. So how much is on the other side? 11.5. Then we landed on 11.5 after a gain of 1.5. So it was 10. And then what did we add to the 7 to get the 10? It's 3. Any questions on our little shortcut there at the end? I think it's a little bit surprising that those differences are exactly the same. Didn't make any difference whether we started at the far left, which was like a nice starting point, -4, or starting in the middle at 1. The difference is the area accumulation, always the same. So go ahead and plot those 9 points and connect the dots. Same, but just pushed up. The area accumulation function, the graph will look exactly the same, but maybe just pushed up by a different amount. When we do an antiderivative, if I just gave you integral of x squared dx. What's the answer? That's a derivative. X to the third over 3. Add 1 to the power, divide by the power. This is another reason these derivative rules need to be really solid, because we are now going exactly opposite. It's so easy to get confused. Is the answer x cubed over 3? Is that the complete answer? Plus c. What does plus c do to a graph? Shifts it vertically. So really, all we're doing is seeing the plus c, different values of c. Yeah, so all of these guys are just vertical shifts of each other. The area accumulation function is in some sense the same as an antiderivative. All right, let's go to number 6. I think we're up to Evan. Okay, so let's try this one. Asking you to find antiderivative of x squared minus 5 dx. So find that. You'll have a plus c. Then find the plus c based on the given information. And check with your neighbors. So we get c is 4/3 after we do our integral. And so that means that the actual function is f of x equals, so I'm just copying this first blue thing here, x cubed over 3 minus 5x plus, and then instead of c, plus 4/3. Okay, and that function right there, I think somebody had mentioned earlier today that we were expecting a cubic looking thing. So let's just take a quick look at that function. So I'm just going to GeoGebra and I'm just typing in f of x equals, just like it says, x cubed divided by 3. What was it? Minus 5x plus 4/3. Okay, so we'll make it a little bigger font. Okay, how does this guy look? So I'm going to try to squeeze it down so it's about the same as the very first graph that we drew. So right here, when we made our first table and then drew our precise graph, we got this thing. Our graph ended up here at 3. Out there at, it was at 4, 3. So let's see how close we were here at 4. Looks like it's maybe 2.5 or something like that. I think we did pretty well. We did overestimate some places. Yeah, so that's the graph. So here's the connection. The area accumulation function is the same as an antiderivative. That right there is an antiderivative. When you did this process with your x cubed over 3, were you thinking areas? When you did x cubed over 3? No, you were just thinking, okay, how do I find an antiderivative? But it turns out it's exactly the same as thinking about areas. Okay, so let's see if we can pull it all together on the next page. There are a couple of challenge questions that I think we'll have some time to look at today, but let's get through the basic stuff first. On the next page, number 1 in the middle, says the key idea of the second fundamental theorem of calculus is that we can construct an antiderivative capital F for any function lowercase f by defining capital F as something that looks very familiar to us now, an area accumulation function starting at some number going up to x. You could start at -4 and go to x. You could start at 1 and go to x. The only thing that would change would be that plus c, so it's the same exact graph, just shifted vertically up or down. Okay, said another way. Again, this thing right here is what? Is that a derivative or an antiderivative? That's an antiderivative. So if I then, for some reason, take a derivative of the antiderivative, we'd expect cancellation, right? You're doing an antiderivative, and then right away you're undoing it with the derivative. So what was the starting function in here? It was lowercase f. So if you take an antiderivative of lowercase f, and then right away you take a derivative of lowercase f, what do you think you'll get? lowercase f. And that's what we get. This theorem says if you take a derivative of this area accumulation function, you start with lowercase f, you get right back to lowercase f. So far. Right, the what? This thing here? Yes. Well, I mean, it's written here because it's part of the theorem. And so I'll give you an example of us using this theorem on the next page, right there. It's asking you to find the derivative of the integral from 1 to x of t cubed dt. So it's part of the problem. But let's go ahead and do this. We're going to do this the slow way, and then we're going to do it the fast way. So the slow way says, well, what should you do first, the derivative or the integral? Integral's inside, right? So we work from the inside out. That's not new. So let's just go ahead and do the integral. So I'm going to copy the integral part. Actually, I'm not going to do that. I'm going to say this is equal to derivative of, and then I'm going to do my integral stuff. So what's the antiderivative of t cubed? Good. Add 1 to the power, divide by the power. Do we need the plus c here? No, because we've got limits on that integral sign, right? That's a definite integral. You don't need to put the plus c because it's going to cancel when we do our subtraction. This thing right here is evaluated between 1 and x. And I'm going to be really clear because there's two different letters floating around here. I'm going to be really clear. We're plugging in t equals 1 and t equals x. And so what we're about to write here is the familiar looking f of b minus f of a. X is just something to substitute in. Yeah, it's a constant with respect to the integral. The variable in that integral is t. Okay, I'm going to copy my derivative because I still haven't done it. And then we're going to plug in. When you plug in t equals x to the red, what do we get? X to the 4th over 4. Yes? Minus, because that's what the first part of the fundamental theorem said to do. Plug in, and subtract. When we plug in t equals 1, 1/4. And now what do we still have left to do? There's a take a derivative. So let's go ahead and take a derivative. Do we need to do the quotient rule on x to the 4th over 4? No. Right, that's really just a 1/4 x to the 4th. So go ahead and take a derivative of that stuff in red. What do we get? X to the 3rd. Okay, that's the answer. It's x to the 3rd. We solved the problem. What function did we start with inside the integral? T to the 3rd. Then we did an antiderivative. Then we did a derivative, and we ended up with x to the 3rd. So the easy way to do this problem is to just say, it's silly to go antiderivative followed immediately by derivative. You start with t to the 3rd, you end with t to the 3rd, except the t changed into an x. That x right there at the top of the integral got plugged in. Did it matter that we were going down here at t equals 1? Could instead of 1, I have put -4? Okay, then this number would change, right? It's only going to change there. And when you take the derivative of it, it's still 0. So surprisingly, it makes absolutely no difference what number is down there at the bottom. It could be a 1, it could be 1 Google. It's going to disappear when you take a derivative, right? Then it's not this theorem. If it was x, you'd actually have to plug it in, and you'd have x's down there. X to x would just be 0. Yep. Good question. So let's do a couple of variations on the theme. First, I want to give you an easy one. So if I asked you, this is not in your page, but we'll just make it up. Derivative of integral from negative 18 up to x of ln t divided by, let's say, sine of t. That's an easy one. I have no earthly idea what an antiderivative of ln of t over sine of t is. So I can't even do it the long, hard way, even if I wanted to. But you don't have to. Theorem says when you see exactly this contrived setup, you just change the t's to x's and you're done. So what's the answer? Ln of x over sine x. All the t's become x's and we're done. You can write it that way too. It doesn't help me in terms of trying to figure out an antiderivative, but it's correct. Easy, right? So if I put something like, if you see some crazy thing on a quiz or test coming up, it is almost certainly this theorem, right? Like don't try, like you see integral sign, I want you to think immediately antiderivative unless it happens to be in this particular form where you say, oh, this is just one of those silly questions where the fundamental theorem makes it a trivial problem. That's the second way. Yeah, the much better way. It feels like you're not doing anything. But if I said, all right, everybody do this calculation. 18 times 53 divided by 53. That's pretty quick. Did he do 18 times 53 and then divide by 53? No. He took it, it's the same. It's the same kind of trick.
So when your brain starts hurting, there's got to be a simple.
It's probably a simple way to do it. Okay, so Andy had asked, what if it's not just x? What if it's 1 over x? So let's go to some variations on that theme. Here in number 8. So first of all, the giveaway that we are using this fundamental theorem is that you have a derivative of a definite integral, okay? Right? That says we're going to be using this theorem. Oh, just one more trick question. If I said this, derivative of integral from negative 7 to 6 of ln of t over sine t. Didn't even finish writing. Topher says 0. It's not this theorem. We have to plug in the top part. No. Why is this 0? Right. That integral is just a constant. There's no x in that integral. So that's just some area. It's some number. Right. So that one is just 0. So the form that we're looking for is exactly what we saw up above, where you have some number going up to a variable. That's the giveaway that we are in this theorem. All right. So one fundamental problem with this made up one over here is that how does that negative 7 trouble you? Yeah, we can't take log of negative 7. So that problem is really, yeah. Okay, so let's try this part A. Derivative of integral of. Okay, I feel the fundamental theorem coming on here. What's the difference between this and the two we did up above? It's reversed, right? The theorem that we did is only good for a number up to x. If it's reversed, you got to fix it. So derivative of, I want to fix it by putting that x upstairs, so I'll just swap them. B. Good. But we pay for it with a negative sign, right? That's our way of swapping the limits. Yeah, technically, it's a good question. You called me on a detail that I was glossing over. Technically, it's in there, right? But if I asked you to find the derivative of negative whatever, isn't it fair to just take the derivative of the whatever and then stick a negative in the front? That's all. That's what I did. That's exactly what we're doing. But you called me out on it. I'll remember that. Okay, so negative all the way out. And so we get our final answer here is good. Questions on that one? It's just a funny little technique. It's not all that useful, to be honest. But it is really interesting that somehow finding the area under a curve has an awful lot to do with undoing a derivative. Finding the area under a curve has an awful lot to do with undoing a derivative. Go back to the very first class of last semester. The derivative was the slope of a tangent line. It has nothing to do with areas. What does it mean to do the opposite of finding the slope of a tangent line? Apparently, it means start accumulating areas. It's really surprising. Okay, what's the problem in part B? Yeah, the top part there isn't just x, it's a function. Plug the whole function in. I mean, that's right. I mean, that's what our instinct says to do. So let's just go ahead and write our answer here. So this equals 1 minus sine, I'm going to write sine of x squared, but sine squared x is probably better. Fine, so we just plug it in. But we have to pay for this one too. It is. Yeah, it's a different cost. Yeah. We don't need L'Hopital's rule. Nikki, what did you say? Nikki says something chain ruling. Nikki, why do you feel chain ruling?
Because there's still stuff to be generalized.
Yeah, there's stuff, right? Yeah. So think about all the basic rules that we talked about last semester. Like we had a rule for x squared. What's the derivative of x squared? 2x. Then we changed it and we made it something complicated squared. And what did you do? You treated it just like 2x. You did 2 and then something, but then times the derivative of the complicated thing, right? Same thing for ln x. What's the derivative of ln x? 1 over x. But then if I give you ln of stuff, you would just do 1 over stuff. That's what we've done. But then you pay for it by multiplying by the derivative of the stuff. So the stuff in this case is sine x multiplied by the derivative of sine x. All right, here is the derivative of sine x, which is cosine x. I need to be more careful about how I've written that. Brackets where? Yeah, this thing right here was the entire derivative rule, like the basic derivative rule is that the whole thing gets multiplied by the derivative of the stuff. That was B. I think we need more space. Yeah. You guys really like L'Hopital's rule. Okay, part C. See if you can try that one with your neighbors. Okay, all the W's become good, right? Just plug in. So 5x squared minus 3x plus ln of 5x squared minus 3x. But now we pay for it by the derivative of what? We're multiplying by the derivative of the thing that used to be x. Not multiplying by derivatives of the w plus ln w. It's just the thing that used to be x and is now something complicated. So we multiply by 10x minus 3. Everything. It didn't have a name. I mean, I don't know how to denote it because it never had a name at the start. That's it. Yeah, I mean, the answer to C, the whole thing from C is equal to this red. Yeah. Okay. All right. Tony, are we ignoring the 21? It feels like we shouldn't, but we do. And it's the same thing that happened up here. When we went from positive 1 there, and then this was a positive 1 here, so that became positive 1/4, right? But then when you take a derivative of that 1/4, what do you get? You get 0. Now, does it matter that it's 1/4 versus some other number over 4? Right? If this was a 21 down here, then there'd be a 21 here, and you'd plug 21 in, but it would just be a number. So no matter what it is, when you take its derivative, it goes away. So it feels like cheating, but it makes no difference what number is down there. Mm-hmm. Great question. Can you give us one, Topher? Can you make one up? Up. Okay, and then in here? I'm going to change it to t in there. Okay. You're just making all kinds of friends today, Topher. All right, can we handle this? Well, the theorem that we had was only good for a number up to x's, right? This is not that. So the only way we can handle this is if we can somehow make it a number up to x. Could add another variable. I'm going to ask you guys to think back to a theorem that we covered a little while ago. A here, C here, D here. The integral from A to B is the same as A to C plus C to B. Agree? You can cut any integral someplace in the middle. It doesn't have to be perfectly in the middle. So how about we cut Topher's integral someplace in the middle? How about we go from 3x squared plus 5 up to, and then we'll make a number. It actually doesn't have to be between. The theorem is true even if c is way outside. Yeah. So how much? 42 of the function 1 minus t squared dt. So that's the one part of the integral. And then what symbol? Plus, and then we do the rest of the region. So we're just still imagining that area there. From where to where? 42 up to x to the fourth. So we split it. Okay, is the second integral one we can handle with our new theorem? Absolutely. Is the first integral ready? No, but we know how to flip it. So go ahead, answer Topher's question. Nice. All right, so we'll come down here. So plugging in, so we go 1 minus instead of t. 3x squared plus 5. And that guy was t squared. And then what do I need to do to that because it was in the wrong order? Negative that, right? So I didn't write switching it, but we know a negative sign will pop out. Oh, thank you. I forgot my derivative of this stuff. Times. What's the derivative of what should be x? 6x. That's the first integral. Plus. And we do the second integral. 1 minus what? Good. Mm-hmm. Yeah, and it's a PDF, and I'm going to post it all over the world. So we're going global with this one. Because I didn't think the first class was as good as it could have been. Okay, questions on Topher's question? So we can handle it. I really like the fact that we looked at this question because it highlights that the theorem that we've discussed today is only good for the specific form that we looked at. A number on the bottom and x on the top. That is the only form it can take. If it takes other forms, we have work to do. If the x is downstairs, what do? We move it up and pay for it with the negative sign. If instead of x, it's something more complicated, a function of x, how do we pay for that? Chain rule times the derivative of that stuff. If it's both functions of x, what do? Split it out and then take care of each one separately. And you can split it anywhere. The 42 made no difference. Oh yeah, I mean you could FOIL out and distribute and then combine terms. Yeah. To be honest, like I said at the start, this is a very contrived thing. And so we're not often going to run into things that have exactly this form. We'll see them on the next quiz, we'll see them on the next test, and that'll be it. So we're not really looking to improve on this. Just want to make this surprising connection that somehow accumulating areas is the inverse process of derivatives, slopes of tangent lines. Other questions on this? Okay, 65 seconds left. I feel badly just scratching this time, but all right, it's like a late Christmas, Hanukkah, Kwanzaa, everything. So enjoy. We'll see you guys. So Math Club is right now.